Okay, good afternoon, everyone. Welcome to today's webinar from the Soil CRC. My name is Michael Crawford. I'm the Chief Executive Officer of the CRC, the Cooperative Research Centre for High Performance Soils. I'd like to begin by acknowledging the traditional custodians of the land on which we meet today, wherever we are in Australia, or indeed internationally. And I pay my respects to our elders past and present. I extend that respect to Aboriginal and Torres Strait Islander peoples here today on our webinar. So, welcome everybody, and we've got a very large audience and quite a, judging by the registrations, a diverse audience and a number of first timers. So in that context, let me take just a minute or so to introduce to you the Soil CRC. Essentially, we're a cooperative research centre funded by the Australian government through the CRC program. Our purpose is to bring industry and research together, in this case, to achieve benefits to undertake research to help to improve the productivity of Australian soils and improve the productivity and profitability of Australia's farms. We comprise 40 participant organisations who contribute cash and in-kind contributions to match that funding coming from the Commonwealth Government. They include 8 universities, 4 state government agencies, 8 industry organisations and groups, and importantly, 20 farmer groups or grower groups from across Australia. And it's the involvement of those grower groups that really helps to drive our end user research that we undertake. We've got funding for 10 years. We've been in place now for 4 years, so still 6 years to go. And we've got quite a number of research projects underway, one of which you'll hear about shortly. In the meantime, let me just alert you to a couple of other events coming up. On the 26th of October, in 3 weeks' time, we'll be having a panel discussion, not a webinar per se, but we'll be bringing 4 or 5 people together in a panel discussion to discuss soil stewardship, how we might reward soil stewardship, good management of soils by farmers, and in turn, how soil stewardship programs might help to incentivise, motivate and reward farmers for the work they do in managing their soils. On the 9th of November, we'll have a webinar by Dr. Jason Condon of Charles Sturt University addressing complex soil constraints. Both of those events you can register for in the same way that you've registered for this event today through our website at soilcrc.com.au. And whilst on the topic of websites, also encourage you to follow us on Twitter, connect with us on LinkedIn, subscribe to us on the Soil CRC YouTube channel. For each of those platforms, you'll be able to stay up to date with the research that's coming out of the Soil CRC and be alerted to events such as this and other webinars and panel discussions that we'll be conducting in the future. This webinar is being recorded, and all our webinars to date have been recorded and are available on our website or via our Soil CRC YouTube channel. So we encourage you to go back and revisit or access our past webinars, and you'll be able to access this webinar in the future. The way this will work, I'll shortly introduce Craig. He'll speak for about 25 minutes or so, and we'll have 15 minutes for questions at the end. And in that, if you want to ask a question, we encourage you to type questions into the Q&A box, and I'll be able to read them out at the end, and Craig will take us through them. So, to today's topic, new sensors for measuring soil. With Dr. Craig Lobsey of the University of Southern Queensland. He's going to talk about some of the research that he's been doing, or a project he's been leading in the Soil CRC on this topic. Craig is a senior lecturer at the University of Southern Queensland in Toowoomba. He has a background in mechatronic engineering and soil science, and currently chairs the International Union of Soil Sciences Working Group on Proximal Soil Sensing. So he's very well placed internationally to talk to this topic. Craig leads a research team within the University of Southern Queensland's Centre for Sustainable Agricultural Systems that focuses on the use of sensor technology to improve our understanding and optimisation of agricultural systems. He has expertise in a range of soil sensing technologies, including electrochemical, spectroscopy, and nuclear methods. So without further ado, I'll introduce to you Craig Lobsey. Thank you, Craig.
Thank you, Michael. Can you see my screen there, okay?
Yes, perfect. Well done.
Awesome.
Off you go.
Thank you, and good afternoon, good morning, everyone, depending on where you are. As Michael said, I lead a project within the soil CRC. It's currently ongoing, this project, but it does cover quite a few bases. We're looking to develop new sensor technology to better map and monitor nutrient status. Quite a challenging task. And as I said, it covers a few bases, a few technologies. And so here I'll give an overview of what we're doing and how we're attempting to solve this challenge or this problem. And so firstly, just a little bit on soil information, or proximal soil sensing. And so the focus of our project is on proximal soil sensing as opposed to remote soil sensing. So here we are using sensors to gather soil information in contact or within close proximity to the soil. And so one of the advantages of proximal soil sensing as opposed to remote sensing is the range of techniques that are available to us and technologies. And so we have a number of techniques which we can use to measure many more properties of the soil, and also the ability to measure through depth, which is one of the key aspects, especially when it comes to measuring soil nutrients. And so over a few years now, obviously this is a fairly well-established research area, but there's a number of techniques out there to measure a number of properties. However, soil chemical sensing remains one of the most challenging and least developed. And there's a few reasons for that. And the reasons include we're targeting specific soil information. And so you'll find that a lot of the sensors we have available to us and are currently in use by farmers or agronomists and researchers tend to measure bulk soil properties. So they're techniques that are relatively easy to use and to measure. And so we get information on bulk soil properties. But when it comes to nutrient management, we really need specific soil information. And there are very few sensor technologies available to do this. Another challenge is that this is a chemical measurement. And so we have to consider chemistry and buffering of the soil. And so that further complicates our measurement. And we also need this information through routing depth. And so this also becomes a challenge, or a significant challenge, especially when we need this information also at very high spatial and temporal resolution. And so this is the challenge or the problem we're looking to address in this particular project. And we're doing this, as I said, we're covering quite a few bases. And so we have three activities within the project. The first one, we're focusing on trying to develop sensor technology to measure soil nutrients, which is obviously a key component to this. But at the same time, it's more than just developing a sensor technology to measure soil nutrients. We need to understand how nutrients move, how they're supplied in the soil. And so it becomes quite a complex situation. And so we're also looking at techniques to better measure nutrient mobility. And so we're looking at using repetitive on-the-go sensing. I'll talk a little bit about that as well. So that's another activity within our project. And also trying to develop sensor techniques that will help us to better measure and understand soil hydraulic properties. And so the idea is that within this framework, we can tie these different sensor technologies together, include modeling as well, and we can develop a framework that allows us to not just measure, but understand how nutrients move through the soil, how the soil supplies or buffers these nutrients as well. And so ultimately we end up with better information that we can use to make management decisions. And so I'll talk a little bit about the first activity. And so here we're trying to develop sensor technology to measure chemical status within the soil. And our focus here, there's a number of different techniques available. You'll see that there are a few in the soil CRC being worked on also. One of these techniques that we can use is electrochemical sensing. And I personally think this is a promising technique. More recently, there's been some developments in this space. And so screen printed electrode technology, and that is what we are basing this current project or work from. One of the advantages is that we can custom fabricate sensors. So using the screen print electrode technology, we can take that and then we can modify these sensors and fabricate sensors that target soil analysis, so specific nutrients. It also enables us to develop rapid, low-cost, integrated sensor technology. And so it becomes very easy to tie these sensors together to measure multiple chemical properties within one system. And so I'll explain that in a little more detail. So firstly, some of the advantages of electrochemical sensing. This is why I feel electrochemical sensors are one of the key technologies that will enable these measurements. Firstly, limited sample pre-processing. And so using electrochemical sensors, we can directly measure in unfiltered soil extract. And so this greatly simplifies the measurement process. We can also accomplish near real-time measurement as well. And so we can measure in this unfiltered soil extract. We can measure in near real time. And so we can monitor things like kinetics and ion exchange reactions that are taking place. And there is useful information in that data also. They become fairly easy to customize for specificity. And so we can have sensors that are targeting nitrate, potassium, sodium, etc. And the sensors are relatively low cost. I'll talk about that in a bit more detail, but they're low cost for the sensor itself, multi-use. And so the single sensor can be used multiple times and multiple chemical measurements, and they require minimal supporting hardware. And so there's been a few developments in this space as well. And so electrochemical sensing hardware in the last couple of years. And so one of those is devices developed by Analog Devices, and we are basing our work around these devices. And so we can develop ultimately a system, a combined sensing system with minimal supporting hardware. There are, of course, like any technique and sensing technique in particular, disadvantages. One of those for electrochemical sensing is sensor calibration or drift. And we are working to get around this point through greater automation of our measurements and automated calibration. And also selectivity. So the sensors themselves aren't perfectly selective. And so they do respond to interferences to some degree. And so this can cause problems, not so much with the nutrient measurement itself, but the compatibility with extracting solutions that we might be using. And so this is part of our research in this project, is fabricating these sensors that target specific ions, and then also trying to determine or evaluate their compatibility with commonly used extracting solutions and reagents. And so just a little bit about how we fabricate these sensors. And so they're based on these screen printed electrodes. So these are tiny or quite small, they're 10 millimeter width and about 34 millimeter in length. And so they're screen printed on a ceramic substrate. And what we do then is chemically modify these sensors so that they become responsive to a specific nutrient or ion in solution. And this involves developing a membrane cocktail, and then we drop cast. The technique is called drop casting onto these sensors. This forms a PVC membrane layer over that sensor, which is responsive then to the ion that we're targeting in solution. As you can imagine, it's quite challenging. This is drop casting approximately 10 microliters using a micropipette onto a very small area, approximately 4 millimeter diameter. But it's relatively easy to do once you have some practice at this and develop skills. And so we can get through and fabricate quite a few number of sensors in one go. The sensors themselves are quite cheap. And so the substrates, the screen printed electrodes, we are purchasing for roughly $5 per sensor. And so considering that they can be used multiple times, this represents very good value for a sensor. And so far, we have focused on developing sensors for sodium analysis, and these have been performing very well. The next, and we consider this to be the most challenging aspect, is trying to measure phosphorus. And there's a few reasons why this is so challenging. And the key reason is speciation. And so the phosphate ion will exist in different forms depending on pH. And so the PVC membranes or the electrodes that we are developing will respond to one form. So one approach we're taking here, and this has been previously demonstrated before in the literature, is the use of cobalt electrodes. And so they'll respond to another form. And so what we are doing is trying to develop a combined sensing system that can account for this speciation. But having said that, it is still very challenging, and it's ongoing work, and we're trying to get around a few problems in this regard. But as the sensor technique itself is largely method dependent, so we get very good results with sodium, and we expected that. So we started developing this approach using sodium electrodes. We expect the same result for potassium and nitrate sensors, and we're currently fabricating these and doing the evaluation. Phosphorus remains challenging, and while we're trying to get around a few of these different issues, for example, the speciation, it always will remain a very challenging property to measure. These sensors, though, they are very low cost and easy to combine for simultaneous measurement of multiple chemical properties in the one system. And they are relatively easy to fabricate. As I said, we're trying to drop cast 10 microliters of solution onto a relatively small area. It does require some skill and steady hands, but with practice, it is possible. We get through a number of sensors, and but we are looking at ways to try and improve the consistency of developing these sensors. And so one aspect we're going to start looking at, or we hope to start looking at, we've recently acquired a few UR5 collaborative robots here at the university within the mechatronics department. And so we're looking at deploying these collaborative robots and seeing if we can use them to help us fabricate more consistently these sensors. And just an overview of the second activity. And so here we're focusing on repetitive on-the-go sensing. And so in particular, EMI, so electromagnetic induction sensing. And so many of you will be familiar with EMI sensors in the form of an EM38 or a Joule-M. And so the aim here, firstly, is to get or extract more useful data from existing and commonly used on-the-go proximal sensors. And so many agronomists and farmers will be using or familiar with the EM38 and also the Joule-M. And so they're fairly widespread in their use. What we hope to get out of this work is more value in terms of the data we get out. And so another sensor we're focusing also is the gamma radiometric, so the MS2000. So we have a Medusa MS2000 sensor, and in a similar way, this is also less commonly used by agronomists and PA consultants, but we're hoping to get more information out of that as well. So what we're trying to do is capture water dynamics through the profile and throughout the growing season at all locations across the farm or the field, and not just at sensor installation sites where we may have installed traditional sensors, buried sensors. And so that is the focus of this activity. And we hope that at least through collecting this data, we extract dynamic data that's changing due to water content, and also the static component of this data. And so at the very least, we get at least better covariates that we can use to interpolate other properties of interest. And so the sensor that we are using here is a Joule-M 1HS. That's what we have here at USQ. And so we have that mounted behind a vehicle, a multi-sensor platform that we use to collect all of our on-the-go sensor data and perform our soil sampling. So the Joule-M 1HS will measure electrical conductivity or apparent electrical conductivity of the soil at multiple depths. And this is driven over the short term largely by changes in water content. There's other soil properties, of course, that will affect this, but over the short time intervals throughout the growing season, it'll be driven largely by changes in water at different layers. And so we hope to get that information through repetitive measurement and deployment of this sensor, not just a one-off survey. The other technique we're looking at as well, we have a Medusa MS2000. And so this is a gamma radiometric sensor. And so this sensor will detect the naturally occurring gamma radiation that's emitted from the soil due to radioactive isotopes of thorium, potassium, and uranium that exist in the soil. What we hope to get out of this through repetitive surveys, and these concentrations typically don't change, but where we do have water, so following rainfall events, we have different attenuation of this signal. And so you can actually see this data where you are doing a multi-day survey using gamma radiometrics and it happens to rain overnight, you will see a sudden decrease in the measurements from this sensor. And so in the same way, we're trying to get more information out of these existing sensors related to water content and movement within the soil, and at high resolution across the field. So an obvious question then is, actually I'll come to that shortly, how we actually go about collecting this information cost effectively. But just firstly, we have a field where we have established a field nearby to Toowoomba from where we operate. And so this is near Millmerran, roughly 60 hectare field. And we have been collecting repetitive data with these sensors over many months. And we've also instrumented this site with Teros 12 sensors. So we have fixed sensor installation, measuring volumetric water content, EC, and also temperature at multiple depths. And so we're using this information to correlate the measurements that we get from the Onthego sensing to changes in water content and other properties. And so this is an ongoing project where we've collected all that data. We're currently analyzing this data and working through it now. And so I don't have any to present to you here, but you're welcome to follow up with me at any point, and I'll be happy to talk about that. And so, as I said before, an obvious question becomes, how do we cost effectively acquire this information, and why are we even considering repetitive deployment of these sensors? And I see robotics and agricultural robotics and developments that are happening in this space as one avenue or a platform that we can use to deploy sensors and collect a lot more data than we currently are. And so that is how we will collect this data, and that is the plan down the track. And this has been happening. So a few colleagues overseas as well have been looking actively at deploying robots and agricultural robots for collecting soil information. And so this is currently a developing active area of research, and our intention as well. And the third activity in the project is trying to develop better ways to sense soil hydraulic characteristics. And so for those of you who have been working in this space, you understand how challenging it is, and time consuming and laborious to measure soil hydraulic characteristics, soil water retention. And so what we hope to do here is streamline these measurements in the laboratory and support the deployment of sensor technology. And so here we see visible near-infrared spectroscopy as one viable way of collecting the detailed information that we need on soil hydraulic characteristics. However, these are limited, or currently limited, by available calibration data sets. And so visible near-infrared spectroscopy requires a calibration data set in order to develop a calibration to predict these properties. And for soil water retention, there is currently limited available calibration data available to us to do this. Another factor to consider also is the requirement for site-specific calibrations. And so this is often a problem where when we're trying to deploy a sensing technique like visible near-infrared spectroscopy at a given site, we require calibration samples from that site in order to develop the statistical relationships between that spectra and the property of interest. And so this means we require a fairly streamlined method of analyzing conventionally, using conventional techniques, the property of interest in order to develop these calibrations. And so our focus in this project and this activity is developing not so much the sensor technology itself, but rather new laboratory methods for high throughput and cost-effective measurement of soil hydraulic characteristics. And so as part of the project, we initially completed a review of different sensor technologies and approaches that are currently in use for the measurement of soil water retention. And our focus on this review was for the potential to automate the measurements and ultimately produce high throughput, low cost measurement of soil water retention. And so we concluded from this review that one of the most viable approaches available to us that can be readily automated and developed into a high throughput analysis is a technique using inverse modeling with non-contact measurement of water content within a soil core that is undergoing evaporative drying. And so this was recently published in 2019, this technique. And so we are developing from that technique. We're looking to evaluate the performance of this technique initially, and we are hoping to develop automation around this technique. As the non-contact measurement that we are using is gamma ray attenuation, and we're using sensors that typically are used in manufacturing or process industries to measure the density of fluids in pipes, for example. And it's an ongoing activity for this year and into next year. Essentially, the way that it works, we have a radioactive source, in this case cesium-137, and a detector, and we measure the attenuation of this radiation as we place a sample in the beam path. And so this attenuation is a function of the soil density and also the volumetric water content. And so what we do then is take a soil core, and as it's undergoing evaporative drying, we are able to move that core up and down through this beam path and rotate so that we can get slices of volumetric water content measurement through slices and different depths within that soil core. And so the idea then that we take this data and we use the inverse parameter optimization and a model such as Hydrus to work back and determine the soil hydraulic parameters that we are interested in. And so this is what we're currently doing now. And so we're working on a system to automate these measurements and provide high throughput analysis so that we can go and sample several samples at a site, and we can load these into the system, and it is able to move through and perform this in a completely automated fashion. And so just to summarize, soil chemical sensing, as I say, this is the focus of what we're trying to do in this project. It remains one of the most challenging and least developed sensing techniques, despite being a critical soil parameter. And there's a number of reasons for this. In particular, the chemistry, the fact that we need to perform measurements and account for the chemistry in the system. We need to acquire measurements through routing depth and also at high spatial and temporal resolution. And so the challenge is, do we develop a sensor that we install in a fixed location and that is able to monitor through time and through depth, nutrient status, where at that location it is unlikely to represent what is happening only meters away. And so that is the challenge that we are faced with. And we see the way to deal with that or solve this challenge is to measure multiple soil properties using multiple sensor techniques and technologies, and ultimately integrate this with modeling so that we can develop not just a measurement at a point location and at a set depth, but rather develop an understanding of how nutrients move through the soil at your particular farm, as well as the status of nutrients at any time. As I said, this is an ongoing project, and so I'll certainly welcome any contact. If anyone has interest in what we are doing, please reach out to me. Thank you.
Thanks very much, Craig. And the opportunity now is open for attendees to ask questions. And you've got Craig's email address there to follow up on. But Craig, I'll open up whilst the questions are coming in. This is talk about the route to market or the pathway to adoption for some of the sensor technologies. What needs to happen next, and how long might it be before agronomists can be using these in the field? That's a difficult one to predict, to be honest. It's I've been trying to develop these technologies for a very long time now. I think with recent developments, it's becoming far more feasible. But yeah, electrochemical sensing, the drawbacks have always been around the requirement for calibration, sensor drift, and the developments we're seeing now with the screen printing electrodes greatly reduce the cost, they reduce the drift. And what we are aiming to do is develop automation around that, and so that it becomes a relatively easy to perform measurement on site. And so, yeah, in terms of predicting how much time, it's a difficult one to say. Okay, thank you. So we've got a question here from Richard Doyle. With the electrochemical sensors, how resistant are they to insertion, reinsertion in soil? And how moist does the soil need to be for them to work well?
Yeah, so the way we perform the measurements, so we don't rely on direct insertion in the soil. We actually collect a soil sample, and this goes into an analytical chamber. And so there we actually add that extracting reagent. We try and emulate as much as possible, standard extracting and measurement procedures in the lab. And so it'll be a 1 to 5 extraction typically. So soil to water or extracting solution, whatever it is that we're using. And the measurement is performed in that solution itself.
Okay, thanks, Craig. Hope that's answered Richard's questions. I'm still the opportunities there for others to ask questions. I'll bring up another question for you, Craig, and take it a little bit left field to a topic we didn't talk about too much in this webinar, but plenty of people are talking about soil organic carbon, Craig. And let's talk, and there's a lot of interest, obviously, from the federal government down. What are some of the opportunities or some of the limitations for measuring soil organic carbon? The question has come up whilst I'm talking. Before the intentional soil organic carbon, thoughts?
It's yeah, well, I think there's fairly established techniques for measurement of soil organic carbon, so visible near infrared spectroscopy. And so some of the work that we did at CSIRO a few years ago in terms of developing a sensor-based method for soil organic carbon quantification or assessment. I'd say that the sensor technology is there for that, in my opinion. But visible near infrared spectroscopy for the measurement of soil organic carbon is fairly well established. And using the same gamma technique actually that I presented here for the measurement of water characteristics can be used to measure bulk density of the soil as well. And so there we can actually derive soil bulk density, the soil organic carbon that we need for the measurement or quantification of soil carbon stocks. The remaining challenge is the measurement of the coarse fraction. And so the measurement of gravel content as well. And finding a reliable, streamlined way to do that.
All right, any ideas about how to best measure gravel in that context?
It's a hard one. It still requires, I think, a fair degree of manual processing of the sample at this point. But yeah, it's a challenging one. Okay,
of course that does vary for soil. So Kanika Singh has asked, are you working on in-field near infrared techniques?
Yeah, so we do. We have an ASD field spec spectrometer here. And so as part of this project, we are relying on that and so we will be doing some three-dimensional mapping, or we propose to do some three-dimensional mapping of many of these soil properties that we're looking at, and visible near infrared spectroscopy will play an important part in that. And so, for example, with our measurements of soil water retention, using the system that we're developing, we will look to develop calibrations to deploy in field for the visible near infrared spectroscopy.
Okay, thank you. Is one of the major issues with phosphorus is not only the 2 ion species, but also the very low concentrations in the soil water?
It is a challenge, but based on our evaluation of the sensors so far, the concentration range is appropriate. And so we have, there's lower detection limits with the sensors, but based on our evaluation within calibration standards, they do cover the range that we need to cover for useful soil measurement. And so, yes, it is right down there, the very bottom end of the measurement range, but it is still within that measurement range. And so, yeah, I still hold some hope for the ion sensor electrodes, electrochemical sensing for phosphorus measurement. But yeah, they definitely cover the range that's required.
All right, thanks, Craig. Now, I'm looking for more questions in the Q&A box, but having said that, there is one in the chat box. So I'll go straight to that one. From David Hine, really important work. The work in developing robust devices for commercial use is challenging and can take as long as the initial research, so it's a very pertinent observation. On the topic of gravel, he's asked about image recognition for gravel as a technique.
Yes, so that is one, and something that we've looked at as well before. Another technique is X-ray CT analysis as well. But obviously, yeah, requirements around the equipment in that case is fairly extensive. But yeah, so image analysis is one that we have considered as well for the measurement of the coarse fraction. But and again, that was actually following some processing. And so yeah, it's yeah, happy to talk about that some more if anyone wants to get in touch with me.
Nice work, Craig. Says Balaji, do these sensors have signal drifting issues over time? How do you rectify?
They do. So yeah, electrochemical sensing, the sensors themselves do drift quite a bit. And so recent developments, and so one of the reasons for that was essentially a water layer forming beneath the membrane of the electrode. But one of the screen printed electrodes that we're using is based on a carbon nanotube. So it's a printed carbon nanotube. And the idea there is that you will reduce those effects. So the drift becomes much less and the calibration frequency becomes less, but it is still an issue. And the way we are getting around that is to develop more automated measurement processes. And so, yes, it's an issue, but we can calibrate out those effects with relative ease.
All right, thank you. Richard's asked a specific one with available water calibrations. So this will help improve the use of infrared methods for each field, or will it be for radiometric field assessments?
Our proposal is, or what we're proposing to do is improve infrared methods. So yeah, visible infrared spectroscopy, that we see that as the technique, as the sensing technique that will be most readily deployed for this purpose. It becomes very easy to measure information at very fine detail through depth and across the field. Yeah, as I said, the challenge is developing calibrations for that technique. And so that relies on having samples that are collected, that have been analyzed in the laboratory using some reference method. And that is where the challenge lies. And so that is what we're hoping to address in order to promote visible infrared spectroscopy as a technique for these properties.
Okay, good, thank you. David Hine has followed up on an earlier comment that Christian Boom at the US Department of Agriculture has calibrated. I think it might be about the gravel. Anyway, David, you can follow up with Craig later on that one. So no more questions. I'll bring in another left field one for you. We didn't talk about it, but soil biology, and most is about the chemistry and the oh, sorry, David was saying about the water and soil. Okay, soil biology. Yeah, there's a lot of interest in measuring soil biology in different ways and relative to chemistry and physical measurements. It's a newer area. Can you make a brief comment about some of the opportunities and, again, limitations in looking at soil biological measurements using sensor technology?
It's obviously a very important property, and so there's a significant interest in developing sensor techniques to measure soil biology. The challenges, though, is it is such a complicated system. So if you consider the soil system and the importance of biology within that system, it is just so complicated. It's so variable, and so you have interactions that are occurring, at very, very short distances near the plant root. It's going to be very hard to capture this information from what I understand and what I see. And so, yeah, very, very challenging. It's going to be a tough one to do, but important. So, yeah, it has to be explored.
Very good. Okay, Craig, I can't see any further questions there, so I'm going to bring the question session to an end, and I thank the attendees for their attention and for their questions. Craig, thank you very much for your presentation and alerting us to updating us on the latest research coming out of the Source CRC in this area for you and the project team, and yeah, the promise of some exciting things to come in this area. Although it could still take a few years before we actually get something that can be held by the agronomist or the farmer in their hand. Okay, so I'll just finish off by taking you back to our website where you can look at details of upcoming meetings, including that panel discussion on the 26th of October and another webinar on the 9th of November. So please show your interest there, register, And again, follow us on the socials, engage with us on the socials, and stay up to date with the latest in the Soil CRC. Without further ado, thank you very much, Craig. Thanks everyone else for your attendance today. And I wish you well for the rest of the day. Thank you.